Yeah. Well.
Okay, welcome everyone to the Jim and Linda Lee Planetarium. As usual, even though this is not a planetarium show, the same rules apply with no food or drink. If you brought anything in, please just leave it underneath your seats. We have a whole series of presentations today. The lights will not be going down completely dark, but if for any reason you have to leave, first please look for one of our ushers. We will have one at each door, and they can help you exit. The doors will lock behind you, and talk to them on your way out. Let them know if you intend to return for the remainder of the presentations. I think that's it, excuse me, for my main announcements. The one thing I want to remind you of is that once the presentations start, there will be a minute for Q&A at the end, and please wait for someone to bring you this mic, because it will make it much easier for everyone to hear your question. Okay, thank you.
Thank you. Welcome everybody to our capstone presentations. We do this every year, and even in the fall if we have people graduating in the fall. So we get to see what all of the senior students in space physics and astronomy are working on in their research, what they completed over the year. So we're happy to have you all. So I'm going to be doing 5 minutes of talking and 1 minute for questions. So I'll give everybody a warning about that. So first up is Roberta Cooper. She's going to be talking about confirming the periodic disk outbursts of the BE star, HD 6226. Okay. Take it away.
Hello everyone, I'm Berta. Before I begin confirming presenting confirming the periodic disk outbursts of the BE star HD 6226, I would like to say thank you to Dr. Knoll. Thank you to all of my professors and colleagues who have helped me. I'm sorry. And also thank you to both my Prescott and Uniloclete families. So classical BE stars are of the spectral type B, meaning they are hot, massive, and very luminous. They also rotate very rapidly with about 85% critical velocity, meaning the point at which the star would begin falling apart. With this fast rotation, they eject material off of its surface, particularly around the equator as depicted in the slide. They do this in order to confirm their angular momentum. This disk is seen in the hydrogen emission lines and infrared excess. In 2021, Richardson et al. Reported possible periodic disk formation, and this suggested behavior might be linked to stellar pulsations. They analyzed approximately 4 years of observational data to look for patterns of disk formation. This behavior followed expectations for viscous decretion disk models. However, is HD6226 really forming a disk, or is it something unusual occurring? For my research, I focused on BE stars gaining and losing their disks. To confirm the periodicity of HD6226, I used the entire database from BESS. With this larger data set, I analyzed about 1,200 spectrum that spanned about 21 years and measured the strength of the H alpha and H beta lines. Then I applied a Fourier transform using period 04, and finally examined the resulting frequency spectrum to see if two frequencies can reproduce the equivalent width versus heliocentric Julian date. This helped test if the disk behavior showed consistent repeating patterns, not random variation. I found two frequencies that roughly reproduced the equivalent width versus date. In the top panel, there is a plot of the amplitude versus frequency for H alpha in the dark blue line and H beta in the orange line. Frequency 1 of 0.01167 is plotted at the red vertical line, and frequency 2 of 0.00539 is plotted at the light blue line. The middle panel is the equivalent width for H alpha versus the date. Each point is one of the 1,200 spectra. The orange line is the best fit line using these two frequencies. The bottom panel is a zoom in of the plot from above between the two red lines. I found very similar results for H beta, but the data were sparser. Here is a side-by-side comparison of frequency, amplitude, and period found in Richardson et al. And my research. I am finishing a publication for research notes of the American Astronomical Society with these results. Thank you, and I will take any questions. Did you want the mic?
Just looking at your results here, and I'm just wondering, just kind of a basic physics question. What are there error bars here that for these results? Or
I didn't have any prepared yet for this presentation.
So I noticed on one of your previous slides, it was a three plot. Yeah. Amplitude, is that exawatts? EW? Exawatts. Equivalent widths, gotcha.
did you get a response? Sorry. Okay, good. All right, well, let's thank Roberta again for the great talk. And next up we have Haley Widger. And Monjambi. Sorry, I forgot it's a double talk. Are you talking about double stars in this double talk? No? Okay. All right. Okay, we are talking about broadband X-ray spectral analysis of symbiotic X-ray binary GX1+4 to disentangle the emission mechanism. I wonder what that 1+4 means.
All right,
Take it away.
I'm Haley, and this is MJ, and we worked with Dr. Pradhan for our capstone project, broadband X-ray spectral timing and analysis of symbiotic X-ray binary GX1+4, and the main goal was to try and figure out what causes X-ray emission.
So before we get into data, I want to quickly introduce what symbiotic X-ray binary are. Symbiotic X-ray binaries are consisted of compact objects creating materials from cool giants, typically in the later K or M types. These systems usually have a long orbital period of 100 to 1,000 days. What makes GX1+4 specifically interesting is that it has a pulsar and an M-type giant, which is a very rare case. And these types of symbiotic X-ray binaries actually make up less than 10% of the total population of all X-ray binaries.
So this is just a plot that shows the long-term behavior of GX1+4. At the top is the bat count rate over several years, starting from around 2005, and the observations that we used for this project are marked in gray. Then is the pulse period over time, and interestingly, it shows that back in the 1970s, when the star was first discovered, it was spinning at about half the rate that it is today, at 120 versus today is 220. And then below is the residual to the linear fit, which just shows that the spin down is not perfectly linear. Then the frequency derivative, which gives us information about how the angular momentum of the accreting material is changing. And then the pulsed GDM, which shows mostly persistent emission with only a few interruptions. And this just tells us that the system is highly variable and dynamically evolving. So because GX1+4 is so variable and the emission mechanism is still unclear, whether it's disk-fed or wind-fed, we performed spectral modeling. So we used 8 near-simultaneous observations from NuSTAR, which uses hard X-rays, and NICER, which covers soft X-rays. And then we tested 3 different models on it. So first is cutoff power law, which is a phenomenological model that is commonly used for high magnetic fields. And then we used COMT-T, which represents inverse Compton scattering in an accretion column, and so it's often associated with wind or column accretion. And then third is PEXRAV, which is a reflection model that represents X-rays reflecting off neutral material and is used to test for the presence of an accretion disk. And then by using these models, we were hoping to determine the physical scenario that best explains the emission. So after testing the 3 models, we found that the reduced chi-squared values for all of the models were very similar, and this suggests that all 3 models fit the data equally well. One possible reason for this is that the source was in a similar luminosity state during the observations. We also found that the absorption and the equivalent width of the iron line don't change significantly. So even though these models represent very different physical scenarios, they produce nearly identical spectra. And this highlights a key issue called degeneracy in spectral modeling, where multiple physical scenarios can explain the same data. And because of this, spectral analysis alone is not enough to determine the true emission mechanism, which is why MJ did timing analysis. And then this just shows all of the upsides and a summary of the best fit spectral parameters used on our analysis. And these parameters just help describe the physical conditions of the system, but again, they're not uniquely distinguishable between the models due to the degeneracy.
So for our timing analysis, at first we tried using both NICER and NuSTAR data, but unfortunately, as you can see with NICER, we could not determine the period, and that was because the observations were too short. They were roughly about 3,000 seconds. And there were also some gaps in between. So in the end, we decided to stick with NuSTAR. And this new star data is relatively new. The first new star observation was taken on July 5th, 2024, and the last one was on July 11th, 2025. So the most important thing about our timing analysis were pulse profiles. But what are pulse profiles? Pulse profiles show how the X-ray brightness of a pulsar changes as the neutron star changes over a period of one rotation of a neutron star. Because the emissions are the magnetic poles, as the pulsar rotates, we see pulsations. It's kind of given us like a lighthouse pattern. So the main features of pulse profiles are peak structures, which is the number of emission peaks and their shapes, pulse fractions, which is the degree to which the brightness varies over a rotation, and energy dependence, which we will talk about more in depth in the next slide. But for the key takeaways of the pulse profiles of GX1+4 is that we see a high variety of morphologies, including double and triple peak structures, which vary with time and energy. What's interesting is that the luminosity remained similar in all observations, yet there was a very obvious morphology variability, which shows that the beaming pattern changes in the accretion. For our energy-dependent pulse profiles, we looked at different energy bands, starting from softer ones, 3 to 7 kVs, versus harder ones, 7 to 15 kVs, 15 to 20 kVs, and so on. We noticed that as soft X-rays get observed, we see a larger change in pulse profile shape compared to harder X-rays, which indicated some sort of material obscuring the line of sight, such as accretion disk. So for our time analysis conclusion, we showed that the analysis of the pulse profile behavior of GX1+4 using new star observation containing multiple epochs and energy bands. We saw clear pulsations in all observations up to 50 kVs, confirming the theory of persistent accretion activity throughout the observed period. The results show that the pulse profiles show significant variability in both shape and structure across different observations, even when the overall luminosity remains similar.
So for the spectral conclusion, all 3 of the models fit the data equally well, which reinforces the degeneracy problem. However, the timing analysis provided some additional insight. So we see that the soft X-rays are more strongly absorbed, which supports the presence of an accretion disk. At the same time, the lack of strong variability in the absorption suggests that the disk may be like optically thin, possibly hot, ionized, or even maybe transparent or transient. And so while we don't have a definitive answer, combining the spectral and the timing helps us to narrow down the possibilities. And then our next step for future work is that we plan to perform a Fourier decomposition of the pulse profiles to better quantify their variability. We also plan to conduct a phase-resolved analysis and examine the variability in shorter timescales. Previous studies have shown that the pulse profile morphology changes over time, which means important details may be lost when averaging out over long periods. So by resolving the data in both phase and time, we hope to better constrain the emission mechanisms and gain a clearer understanding of the system.
I know that the timing and pulse analysis shows different profiles, but has there been any constraints yet on pulse delays that may happen due to orbital motion in the system?
currently, not to my knowledge, but that's definitely something that we can look into.
So I see in your conclusions that you were saying that there was more absorption of the soft X-rays. And so I assume that's made from, I mean, you have two different measuring devices. You have the NICER and NuSTAR. Do you know if the systematics are the same between them that you can draw that conclusion?
Well, for the NICER, we stopped working on it after we couldn't determine the period. So we only have the information that we presented was mainly just from NuSTAR.
Okay. So you took both soft and hard from one source?
Yeah.
Okay.
Okay. Thank you very much for that great talk, Neutron Stars. Up next is Guru. And Guru is going to talk about understanding orbital variability of SEN X3 using NICER 1. Okay, it's not any of these? Yeah. Sent out the email yesterday. Oh, who was the email sent to? I think it was Susie. Susie? Whoever was reaching out for the email. Susie, did you get an email from Guru? I did not. Oh, okay. You know what we could do is technical problem. We'll come back to Guru in a minute, and let's go on to Jack Hedberg. Come on up. And now for something completely different. So Jack Hedberg's going to talk about gravitational waves. Gravitational wave signatures and prospects for detecting quantum gravity effects. Cool.
Hello everyone, I'm Jack. I'd like to talk today about quantum gravity effects and gravitational waves. So this is something I've been working on with Dr. Zanlin for a few years now. So just as an introduction as to what I mean by the quantization of gravity, the quantization of a force generally refers to the moving of a theoretical framework for force from a classical model to that described by quantum mechanics. For the strong, weak, and electromagnetic forces, we have this in the standard model of particle physics. Gravity, there's still no universally accepted way in which we have completely figured this out. So, a couple of the problems with why this is so much more difficult with gravity, it's mathematically speaking, it's much more different and difficult. As in addition, gravity is a comparatively weak force compared to something like the strong force. It's quite weak, so any particle that would mediate it would interact much more weakly with its surroundings as well. And so, let's see. So how me and Dr. Zanelin are approaching this is that the direct detection of gravitons is generally accepted to be nearly impossible. There's a interesting paper by Freeman Dyson that talks about this. How me and Dr. Zanelin want to go about this is that the detection of any collectical statistical behaviors that large groupings of gravitons may have has not yet been ruled out. So we're hoping that how we can do this is that there are many discrete particles like photons that show a Poissonian distribution in their arrival times in the detector. So we're hoping that if gravitons exist, they would also be subject to this behavior, and that we would see fluctuations around our classical model in LIGO. So the role that LIGO has to play in this is that we've gotten pretty good at seeing gravitational waves. We have a lot of events now. So the amplitude of any gravitational wave we would see would depend on the incoming number of gravitons that interacts with the mirrors of the interferometer. So what we're trying to ask is how big these small variations would be and if it's reasonably possible to see them with LIGO. So I have to talk about a little bit of theory now, so I'll try to get through this. So the first thing that me and Dr. Zanelin have been doing is that we need a useful parameterization for describing how gravity would interact with the interferometer mirrors on a quantum scale. You can do this with something called Palantini action. I'm not going to talk about this too much due to time, but it exists, and with it you can get a fairly good Hamiltonian for your interaction. And secondly, we can use a tool called quantum Fisher information. This measures how sensitive an interferometer is to a change in any parameter. So with this, we can then, sorry, I lost my train of thought there. But with this, we can measure how strongly the quantum state of the interferometer responds to any physical parameter change in the gravitational wave. So from here, you can get something called the quantum Kramer-Rao bound. This establishes a lower limit to how sensitive any instrument can be. So from this, if you can calculate how big the fluctuations around the classical model in the gravitational wave are, you can establish whether or not those are actually big enough to be seen by any interferometer. So in the future, where we want to go with this is that we have our Hamiltonian, and so we want to choose a waveform for a gravitational wave source. And from that, we can compare our results via the quantum Fisher information to get to the quantum Kramer-Rao bound, which gives us an estimate of whether or not these effects can be seen in LIGO or any other interferometer. And just a couple of last statements. I'd like to thank Dr. Zanelin for working with me on this, and thanks to Ricardo Escobenda, who's a postdoc at the University of Guadalajara, who's put a lot of work into this as well, and whom we have talked a lot about regarding this. So that's all I have. If there are any questions.
Thank you, Jack. So just a quick question on what you're calculating some different quantities. I'm just wondering if you have a sense of what you're going to what part of the data you can compare to any kind of like prediction or formula you might have.
Okay,
What are you actually trying to measure to show quantization?
So perhaps I can clarify this a bit. So what we're trying to do is that I mentioned the Kramer-Rao lower bound. What this would establish, if we can calculate it, is it's just a baseline for how big our signal would need to be in order to be seen. So if we can get to that, then that would just be a starting point to tell us whether or not this is a viable option for actually looking at any signal at LIGO for these small changes, if that makes sense or answers the question.
Okay, so I think we're going to go back to Guru if... Okay. Okay, looks like we got the talk. So again, Guru's going to talk about understanding orbital variability of SEN X3 using NICER 1. Okay, take it away.
Hello, everyone. Can you guys hear me? So I'm Guru Balakrishnan. Here's my thesis that I worked with Dr. Pratt on. So we're trying to just be going through the introduction, talking about what is SNX3, what is NICER, methodology, results, analysis, conclusion, future work, and references at the end. Introduction for what is the X-ray binary? X-ray binaries usually have a neutron star or a black hole orbiting around a larger companion star, which rips matter off of the larger star, forms accretion disk around the neutron star, and this X-ray binaries usually provide natural laboratories for studying matter under extreme conditions, especially like gravitational and magnetic conditions. In this research, we used orbital monitoring observations of SNX3 to study how X-ray flux, spectral properties, and pulse profiles vary across multiple orbits. And by examining both phase resolved and light curves of spectral behavior, we aim to resolve changes between accretion flow and geometric effects, such as observational or partial occultation within the system. So what is SEN-X3? SEN-X3 is Centaurus X3, which is a high-mass X-ray binary, which has a neutron star specifically, and a massive O-type supergiant star orbiting each other, also known as Kremensky stars. Sorry, my pronunciation. And this is an X-ray pulsar with a spin period of 4.84 seconds and an orbital period of 2.08 days. The mass transfer occurs through Roche lobe overflow, which forms an accretion disk around the neutron star. And NICER is known as Neutron Star Interior Composition Explorer, aboard the ISS since 2017, been used to observe various X-ray binaries. And observes in the soft X-ray band with high timing and spectral resolution. Methodology, we looked at 7 NICER observations across 3 consecutive orbital cycles, usually spanning the set of data that I looked at was spanning between the 11th of February to the 17th of February back in 2024. We processed the data on SciServer, which is, or using NASA's NICER pipeline on SciServer, which is a cloud computing platform. Looking at the spectras, we fitted each individual spectras with a black body plus power law continuum model with multiple continuous and absorption lines to characterize thermal and non-thermal emission lines. Results, in the top right image, that is an individual spectra that we looked at that is fully fitted with the black body and the power law model. At the top, that's the main spectra, and the very bottom part of that part is the chi analysis that shows how well the model has been fit. And once we fit all 7 of the spectras onto one graph, which is the guy in the bottom over here, they're mostly identical. The only major difference is the flux is slightly different. So 7 fully processed spectra are overlaid on this bottom and right image, showing clear flux differences while maintaining overall spectral shape. The fitting parameters were then used to examine trends across orbital phase and luminosity. So using the fitted parameters we get from these 7 spectras, we were able to conclude, or we're able to see like there's a strong modulation in X-ray brightness with dimming inside of the eclipse and brightening outside of them. And then also, despite luminosity changes, most spectral parameters remain relatively stable across observations, and primary emission mechanisms does not vary over the emissions. For example, the specific one one of the few ones I want to mention are iron 1 and iron 25, around 3.9 MJD, which is over this way. So this is the 3rd up and the 4th up, right around this portion right here. You see the uncertainty values are pretty high on that one, so there's like a little bit of uncertainty in that. And that despite the rest of the parts that we analyzed was all in, are pretty accurate, except for those. And then another one that we're looking at is iron 25 and the K beta over here, around the 5.3 MJD. So that also has a lot of variation for whenever we fit those. Either we can reprocess how the data fit or the model fits, or we can try to include more nicer data, or so for example, either CRISM or New Star observations to see if that further refines the model. And this also proves orbital variability is dominated by geometric effects rather than intrinsic changes in the emission mechanism. And any questions?
Okay, thank you, Guru. We don't have that much time for a question. Maybe one question. We have one right here.
So what parameters did you use, and how did you fit them to the spectra?
For example, looking at the obs ID over there, there were around like 30 or so parameters that we're trying to process them through the XSpec pipeline on Sci server. There's 30 or so parameters. There's 10 or so individual parts we're trying to fit, which each of those parts have a line, norm, and sigma, which kind of varies how the fit aligns with the model, or the model aligns with the data. And freezing and thawing each of these parameters, trying to run it again, multiple iterations and cycles through, that further refined, and we got certain parameters, and that's where we were able to compile them on this pretty gnarly looking graph over here.
Okay, thanks for the question. Thank you, Guru. And we're going to keep moving along here. So next talk is William Punches. He's going to be talking about a first orbit for the binary Wolf-Rayet LS3 plus 4421. Oh, those astronomers and their star naming schemes. Go away, William.
Perfect. Hello. Okay. Yeah, my name is William Punches. I'm going to be presenting a first orbit for the binary Wolf-Rayet system LS3 plus 4421. So, first off, what is a Wolf-Rayet star? They're massive, typically evolved stars. This is an okay demonstration of what one looks like. Wolf-Rays have really powerful stellar winds, so they typically are much more like optically dense. They don't really have like a photosphere like most stars do in the traditional sense anyways. So this particular system is a binary. It was identified by Marin et al. In 2024 as a O6.5 main sequence star with a WN6 companion. We have gotten additional data. This system was observed by NASA's Transiting Exoplanet Survey satellite. It was observed in 6 of its sectors. We also got 7 Maroon X spectra and started trying to model it in Phoebe, which is a Python modeling program for like modeling binary star systems. So this is what the test data looks like. You can see all of the sectors overlaid here on this side. You see these really consistent regular eclipses. This is actually a really clean, nice light curve for a Wolf-Rayet that tend to have a lot of additional variability. This one's relatively clean. When you phase the data to the orbital period of 4.43 days, you get this really nice light curve. You get the O-star eclipse, you get the Wolf-Rayet eclipse, and you also get this like other feature that pops out that we'll talk about a little bit later. So spectroscopy-wise, this is the hydrogen. I shouldn't say hydrogen alpha. Technically, it's like some overlapping hydrogen and helium features. This one was measured for its velocity, although it wasn't used for the like modeling of the radial velocities because it's very heavily contaminated by the Wolf-Rayet wind. So instead, we look at the 5411 line, which is much less contaminated. We grab some velocities out of that. We also, in the course of modeling this, we're really struggling to get it to properly model in Phoebe. Like it just, the system's mass didn't seem to be lining up with what the model in Phoebe was wanting to do. And so we took a look back at this data that was from the Marin et al. Paper, and we specifically looked at these nitrogen features. Now, these are the nitrogen features that you use to identify the class of the Wolf-Rayet. They are also features that can show up in an O supergiant. So essentially what we thought we might have here is maybe we have an O supergiant with a Wolf-Rayet. That pushes the Wolf-Rayet to an earlier type. So instead of a WN6, maybe it's a WN5 or a WN4. And that pushes the O star into the supergiant regime, lets the mass go up, which increases the distance between the stars, which decreases the tidal forces, which seems to be working better with the Phoebe model. So maybe it's an O supergiant. What we need to prove that is we need some additional data that goes further out into the blue. The Maroon X spectra doesn't quite go far enough into the blue. These are little nice 5411 velocities. The ones for the Wolf-Rayet, we don't actually believe them. We think they're also pretty heavily contaminated. Essentially what you get in systems like this is, and it comes up a lot better in this plot. So this is that H alpha feature we were talking about. You may notice that it's actually offset in phase from the O star. This is not typical for, like you wouldn't expect this unless there's some additional effect going on in the system. So what we think is going on is basically this line is forming kind of in, it's forming further out in the envelope of the star, which means that when the winds of the two stars collide, you get an excess on one side. And that's why you see this offset in phase. And you also sort of see that the offset in phase is a little bit lined up with that third eclipse. We think that might be related to colliding winds in the system. So we've got a little Hubble proposal going on right now because we also see similar tertiary features in 3 other Wolf-Rayet systems, one of which is V444 Cygni, which is essentially a clone of LS3 plus 4421. It's a very similar system. So yeah, in the future, we want to get better kinematics. We want to get specifically kinematics on the nitrogen lines that are further out. And we'd like to do that with Hubble as well as a simultaneous Gemini spectra, because that will give us the like really good data that we need to really nail down these parameters and the velocities of the stars. So yeah, that's everything.
Thank you, William. And we have a little bit of time for one or two questions. Oh, we got one in the back.
What does WN mean?
Oh, yes. Okay. So Wolf-Rayets come in a couple of different flavors depending on the abundance of certain elements. So you can see carbon-rich Wolf-Rayets, nitrogen-rich Wolf-Rayets, and oxygen-rich Wolf-Rayets. So in this case, the WN is signifying that this is a Wolf-Rayet whose nitrogen features are stronger than its oxygen or carbon features.
Okay, so next up is Dante. He will be talking about the variability of BE stars in the Pleiades as observed by TESS. All right, go ahead.
All right, so I'm Dante, and I'll be discussing the variability of BE stars in the Pleiades as observed by TESS. So first, I want to knock off what exactly is a BE star. They are a subclass of B star, signified by their rapid rotation. They typically rotate at about 90% critical speeds, where 100% would overload its gravitational binding energy, and these stars could potentially tear themselves apart. Since these stars rotate at a lower threshold, all that happens is they get sort of elongated towards the equator and they eject material in a disk. This ejecta just orbits at the equator, and we typically see these features as emission lines in the spectra. So in the Pleiades in particular, there are 7 primary stars, 4 of which exhibits this behavior. You can see that Pleione, Alcyone, Merope, and Electra all have peaks in their spectra where there would otherwise be absorption lines. So Atlas, Maya, and Taygeta, they all have dips in their flux at the 6,650 angstrom wavelengths, whereas Alcyone, Pleione, Merope, and Electra have peaks in their flux. And these peaks and flux are trademarks of the BE star class. To gather data on the Pleiades, we used the Transiting Exoplanet Survey Satellite, or TESS. And TESS was made to observe exoplanet candidates by observing stars and how their flux decreases as their satellites transit. TESS offers a guest program so that researchers can use the services to gather other data that's not a mission-critical mission. For Pleiades, we used existing TESS survey data and found new candidates for the Pleiades members. So if you actually look at the graphic on screen, up towards the top left are blue dots. That is our current model of the Pleiades, whereas everything in yellow shows new potential candidates for a greater Pleiades structure. And the 4 stars I am dealing with, Pleione, Merope, Electra, and Alcyone, are part of the overall core structure in the Pleiades. So starting off with Pleione, we see that we have our light curve. It's very oscillatory in nature. And performing a Fourier analysis on it shows that we have a vast dominant frequency in the 1.75 cycles per day regime. On the left, we have 3 graphs, the top one being the light curve and a smoother extrapolation of the data to denoise it. In the middle is the observed data subtracted by the actual a denoised light curve. And at the bottom, we have a more smooth version to allow for a more granular idea of what the light curve looks like. For Merope, we see a very similar situation where we have a vast dominant frequency, but this time at the 2.05 cycles per day frequency. And it's very similar in shape, since we just have effectively one frequency. It's very sinusoidal, and the denoised light curve matches that. Electra is a little bit different in that it has two dominant frequencies, one in the 0.9 cycles per day regime and one in the 1.8 cycles per day regime. Since they are harmonics of each other, you end up getting this nice light curve where you have a larger peak and then a smaller peak following it. And since they are harmonics, they don't really destructively interfere, and so you get this nice phasing as the light curve goes on. Alcyone has three dominant frequencies. One of them is in the 0.44 cycles per day. The other one is 0.86, and the other is 1.3. Since 0.04 and 0.08 are harmonics of each other, they have very good phasing, which sort of blocks out the 1.3 cycle. So you don't really see that much destructive interference. As for Pleione, it shows some very distinct behavior in its H-alpha lines, where the changes in the H-alpha equivalent widths change with time. And it also correlates to a change in flux. As the equivalent widths for H-alpha increase or decrease, the flux matches that as well. I am currently in the process of finishing up a paper to submit to JAA VSO, which will go more in depth about the observations tests made for Pleione, Merope, Electra, and Alcyone. Thank you.
Thank you. And we got time for maybe one quick question. Okay, I don't see any. I'm going to ask a quick question. The data you got for those 3 stars, what can you learn from that, or what do you plan to do with that?
So BE stars by their nature are very temperamental. The disks that orbit the stars, they come and go as the star interacts with its medium. The flux that we are observing is directly tied to their emission lines in the disks. And because these disks come and go, you can correlate that to how the light curve changes. So you can see just how active these disks are and whatnot.
Okay, thank you very much. Thank our speaker again. And we are almost at 1, but we have one more talk. And since some people are leaving, I'll just say ahead of time, congratulations to you all. Thank you for speaking. And congratulations on graduating 2 weeks from now, or 3 weeks, whatever it is. Awesome. So let's get our final speaker, Joe. Let's get him set up. Joe's going to talk about an exploration of a bipartite gravitational wave detection.
Should I actually present this? Sorry, I don't know Adobe. There we go.
There we go. Hopefully that will, yeah.
Okay. Thank you, Dr. Bailey. Okay, so I'm Joe Robato. I'll be talking to you about a new method of, or a new technique for detecting non-classicality in gravitational waves. I have two goals with this presentation. The first is to give you an idea of what bipartite detections are and how they might work. And the second is to convince you that this technique needs more attention from the physics community. Just before we begin, I want to say thank you to, I don't know, is it?
Yeah, it is. I guess, hold on.
Hello? Hello? Okay. Before we begin, I want to say thank you to my research advisor, Dr. Jones, and my collaborator, Logan Finke. So let's get into it. On the left here is the late Freeman Dyson. Back in 2013, Dyson argued that individual gravitons would not be practically observable if they were observable at all. Despite this, current research into the detection of non-classicality has primarily focused on single-point graviton detections. But this neglects the fact that many of the most prominent quantum properties will emerge as the result of interactions between multiple particles. So clearly there's a need to examine how these multi-particle systems behave. And an example of this idea of using multiple particles to detect non-classicality, there's this famous experiment in the field of quantum optics. It's called the Hanbury, Brown, and Twiss experiment. Some of you may have heard of it, some of you maybe not. Essentially, they were able to determine that light has statistical properties which couldn't be explained by classical models. And a diagram of their setup is on the right, but what they were really looking at is photon correlations, specifically the second-order correlation function. So put simply, the second-order correlation function is a measure of how likely two events are to occur together. I've written it here in terms of the intensity of the light at detectors 1 and 2. And this function has some interesting properties, which we can use. If you evaluate the second-order correlation function and you find that it's equal to 1, that's something called coherent light. This is a classical effect, it's very well understood. If it's greater than 1, that's something called bunched light. This is a bit unusual for a classical system, but you can show that given certain conditions, this can be produced by classical effects. Where things get interesting is if the second-order correlation function is less than 1. This is a phenomenon called anti-bunched light, and there is no known classical effect which can cause anti-bunched light. So this is a signature of non-classicality. Now, I've been talking about light and photons, but you could also apply this to other bosons like the graviton. And so you could imagine creating some sort of Hanbury, Brown, and Twiss experiment to detect anti-bunched light in gravitational waves. Okay, great. But can we actually expect to see these results, these effects? So let's try to inform an answer to that question now. This is on the left just a diagram of a typical interferometric detector. It's very simplified. And from this point forward, I'm just going to skip over a lot of the math because I don't think that's particularly interesting. What's really interesting is the results. And so starting with the geodesic deviation equation, we derive this expression for the mean graviton number, which is the number of gravitons interacting with a detector for one cycle of the gravitational wave. Plugging in some typical numbers, that comes out to 3,034 gravitons, about 3,034 gravitons. And that's a low number, which is interesting for reasons that I'll get into. But by itself, it doesn't tell us very much. What we should really be looking at is the efficiency of the detector. And again, I'm skipping over some details here, but the efficiency of the detector is on the order of 10 to the negative 31, plugging in those same numbers from before. So why does that matter? Well, these low detector efficiencies are hardly surprising considering the nature of gravitational wave detection. In fact, low detector efficiencies is one of the biggest challenges for any single-point graviton detection scheme. However, if we take another look at our second-order correlation function, we can see that each of these intensity terms is actually proportional to the efficiency. So we can pull out an efficiency squared from the numerator and denominator, and this is just equal to 1. So the efficiencies cancel out. And this sort of implies that for bipartite detections, low detector efficiency will not be as big of an issue as it would be for a single-point detection. Additionally, that low particle number that we were talking about before is incredibly useful because a property of the second-order correlation function is that it will always approach 1 as particle numbers increase due to random variation in the sample. And this has the effect of obscuring non-classicality. So it's very important that we have that low particle number. Now, if there's anything I want you to take away, it's that bipartite detections are a promising alternative to single-point detections for revealing signatures of non-classicality in gravitational waves. A major challenge to single point detectors is the low the low efficiencies associated with detectors, but we have strong reason to believe that this will not be the case for bipartite detections. And in fact, those low efficiencies may even be an advantage because of the low particle numbers that they cause. I'll also note that statistics are going to be a big issue for any gravitational wave detection because the signal strength is just so low compared to all the noise from the background. Now, I have not personally done any statistical analysis to see if these effects are statistically significant for current detectors. So there's a lot of work to be done. And that's why it's so important that we get this idea out there and we get a lot of people in the community thinking about bipartite detection seriously. So thank you for listening. I think I can take questions. I'm not sure how I did on time.
Okay, thank you very much, Joe. Let's thank Joe. Yeah, we got time for at least a question. If you have to go, that's fine, but anybody have a question for Joe? Jack? This is related to your talk. Do you have a question? Okay. Yeah, okay, let me maybe start that conversation. So single point detection is not likely or maybe ruled out. What about detecting a whole bunch of effects from a bunch of gravitons at one location rather than two locations? Maybe that's what Jack is working on.
That's definitely an avenue you can explore, but I would argue that if you have a bunch of gravitons, they're going to be interacting with each other. So it's still beneficial to take a look at what those interactions would look like. So this is definitely something that needs attention regardless.
Okay. Thanks, Joe.
Thank you again.
Thanks. Well, that concludes round one of the capstone presentations. Thank you very much for coming, and thank you very much to all our speakers, and congratulations. You're going to be graduating in a couple weeks. We'll have round two next Tuesday with 7 or 8 speakers at that time, and we'll try to get some donuts for that as well. So please come to that on Tuesday, support our graduating seniors, and I'm sure if anybody wants to come up and talk to them, they'd be happy to talk to you after this is over. So that's it, folks. Thanks for coming. Have a great day. Maybe see you next Tuesday.
Thank you all for coming. Please exit the opposite way that you came in. So you came in on the right side. Please exit on the left side of the theater. Thanks.